All right, guys, it's 10 o'clock, so we're going to get started today. I want to welcome you to the Week 8 AP Physics 1 content review session. Please mute your mic and turn off your webcam. That just makes Google Meet work better. If you have a question, we want you to unmute and ask it. We welcome any questions you have. We are recording this session, and that recording will be posted to the A+ College Ready Science YouTube channel. If you've never checked out our channel, make sure you do that. There's all kinds of resources that will help you get through Physics 1. Next week's session, week 9, will be held at 10 a.m. on Friday, October 23rd. And that will be the last of our weekly content review sessions, at least for this semester. In spring, we'll have lots of review sessions as we start to get near the AP exam. So today, our session is going to review both Units 1 and 2. Most of you are probably working through Unit 2 right now. So we're going to do a little bit of review of both units. So I think we have 12 questions we're going to go through. So here's the first one. A ball is thrown vertically upward from the ground. Which pair of graphs best describes the motion of the ball as a function of time while it's in the air? Neglect air resistance. Now notice some of these are looking at y graphed against t. So that would be like a position time graph, or you could think of it almost like this position time graph, displacement. So you're looking at displacement. Other graphs are acceleration versus time. Still others are velocity versus time. So you've got to look really, really closely at what's going on. And let's just sort of start with choice A and work our way through some of these. So A is showing that the ball goes up, 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 evens out, and then comes down. Well, that sort of makes sense, right? That looks okay. And then A here, the A versus T graph is showing that the acceleration is changing over time. And the acceleration starts out up here with a positive value and then goes down, down, down until it gets to a negative value. I think you guys know that this is not correct. This one looks like it might be okay, not so much on this one. So A is not a correct answer. Now let's look at B. So B is showing position going up and coming back down. Again, not curved, but that's okay. Now let's look at this one. So it's showing our acceleration again is starting with some positive value, going down, 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 getting to 0, and then going back up. Well, I'm hoping you guys know that that cannot be correct. So now let's look at C. Let's start off by looking at the acceleration time graph. It's showing that the acceleration is a constant negative value. And I hope you guys know that that means that that acceleration is essentially negative 10 meters per second squared. It's g. It's acceleration due to gravity. That's what's happening throughout that whole entire problem. We're neglecting air resistance. So all of the acceleration is due to the acceleration due to gravity. The velocity time graph is showing us that we're starting with a positive velocity, going up, and that over time that velocity decreases down to 0, and then it starts to accelerate in the negative direction until we get to a negative velocity. So this looks correct as well. Our answer here is C. All right, so here's question 2. This is a ranking activity. This is sort of like some of you have probably done the typers ranking activities in class. Same kind of thing here. So this says we have projectiles launched on horizontal ground with the same initial speed. So they come out of the cannon or whatever's launching with the same speed. And we want to rank them. So the first one, rank the situations from least to greatest in terms of time the projectile is in the air. Well, I'm hoping you guys know that the time in the air is determined by the vertical component of the velocity, of that initial velocity. So let's figure out which one of these has the greatest vertical component. And I'm hoping that you see that D is all vertical. There's no horizontal component to that velocity. That means that one's going to go straight up. It's going to stay in the air the longest. Well, this one's the next most vertical. So it's going to stay in the air the second longest. This one's the next most vertical. And then this one is the least vertical. So it will hit the ground first. So from least to greatest, A, B, C, D. All right, B. Rank the situations from least to greatest in terms of the horizontal distance traveled while in the air. All right, well, first of all, you guys, I hope, know that that one goes straight up. It doesn't go horizontally at all. So it's definitely going to be the least. What I'm also hoping that you know is that a 45-degree angle always is going to be the one that gives you the greatest horizontal component, or the greatest horizontal displacement. And the one that most approaches a 45-degree angle looks like A to me. So it's going to be the one that goes the greatest distance, the greatest horizontal distance. B is the next closest to a 45. And then C is pretty vertical, so it's not going to go very far horizontally. So C is going to go right there as the second least horizontal displacement. Next, rank the situations from least to greatest in terms of the vertical distance the projectile travels. So how high is it going to go? Well, obviously, D is going to go the highest because all of its velocity is vertical. C is going to go the next highest because it has the second greatest vertical component. B would be next, and A would be the least in terms of vertical displacement. Finally, on D, rank the situations from least to greatest in terms of the acceleration of the projectile while in the air. We'll notice that we're ignoring air resistance, which means that the acceleration is caused by gravity. The acceleration of all of these objects should be a vertical acceleration of g. So they all have the same acceleration. It's the acceleration due to gravity. So we're just going to check right there. All right, that's it for question 2. Now let's move on and let's look at 3. 2 children on the playground, Bobby and Sandy, travel down slides of identical height but different shapes. The slides are frictionless, assuming they start down the slides at the same time with 0 initial velocity. Which of the following statements is true? All right, so what I'm hoping that you see here is that Bobby's slide starts off steeper, which means Bobby's going to have a greater acceleration to begin with. Sandy's slide is not quite as steep. That's telling us that Bobby, he's going to get to the bottom first because he starts off at a faster speed. So Bobby reaches first. So it's going to be A, B, C, or A, B, or C. And what I'm hoping that you realize is because of this steepness here at the beginning, Bobby has a higher acceleration. His acceleration is closer to G. So our answer here is going to be B. And by the way, these problems are from Dan Fullerton's website. If you're looking for practice problems for AP Physics 1, just Google Dan Fullerton and you'll find a host of videos and practice problems, and they are all great quality. All right, so here's one we got to do some thinking about. So an eagle flies at a constant velocity horizontally across the sky, carrying a turtle in its talons. The eagle releases the turtle while in flight. From the eagle's perspective, the turtle falls vertically with a speed of v1. So let's say here's the eagle. He's still moving this way. He drops the turtle. Well, the turtle's fallen, but the turtle also has the same horizontal velocity that the eagle had. So the turtle's falling like this. The eagle's flying like this. An observer on the ground over here is going to see both of those. So what we want to know, if the turtle falls with a speed of v1 down from the turtle, and if the observer sees the turtle moving essentially like that, because to the observer, the turtle is coming toward the observer and falling. That's V2. What is the speed of the eagle with respect to the observer on the ground? So essentially, we're looking for this. What's that horizontal speed of that eagle? Well, notice that we have a nice right triangle here. Here's the turtle's downward velocity, and here's essentially the turtle's net velocity. And we're looking here for the horizontal component, which came from the eagle. So we can just use the Pythagorean theorem here. We'll call this x, and we'll say x squared plus v1 squared equals the hypotenuse squared. Solve that out for x. So x squared is going to be equal to v2 squared minus v1 squared. We need to take the square root of both sides. And when we do, we end up with x equals the square root of v2 square minus v1 square. And that looks like it is choice D. So that's working with vectors and realizing how to break a vector into components or add vector components together to get a resultant. All right, next we've got a cargo plane flying horizontally at a speed of 140 meters per second. So this guy's going like this. He's at a height of 50 meters above the ground. So here's the ground. Got a vertical distance here of 50 meters. A supply package is dropped out of the plane at time t equals 0. 2 seconds later, a package is dropped out of the bottom of the plane. Air resistance is negligible. What happens to the separation between the packages as they fall through the air? So over here, package is dropped. We'll draw it as an X. And then 2 seconds later, when the plane's over here, he drops a second package. Now, the horizontal distance between them isn't going to change because horizontally, they're both traveling at the horizontal speed of the plane. Both of these boxes will travel horizontally at this speed, assuming that we ignore air resistance. Vertically, though, we've got to think about the distances vertically. This box was released first, and it was released 2 seconds before this box. That means it had 2 seconds to accelerate that this box didn't have, which means this box is going faster than this box. And because box 1 is going faster than box 2, over time, the vertical distance between them gets bigger and bigger and bigger. So our answer here is B. The separation between the packages increases, and that's because box 1 was released first. It had more time to accelerate, and therefore it had a higher velocity throughout the whole time interval. All right, so here's the same setup on question 6. This time we want to know how far apart will the packages land on the ground. So again, let's say box 1 was dropped here. Box 2 was dropped over here. The plane's traveling at 140 meters per second, which means the boxes are traveling horizontally at 140 meters per second the whole time. It doesn't matter if they're in the plane or falling from the plane, as long as we're ignoring air resistance, their horizontal speed throughout this whole problem is 140 meters per second, which means horizontally, the distance doesn't change. So what we're looking at here is that they're going to land apart essentially 280 meters, because during that 140 during that 2 seconds, the plane traveled a distance of 280 meters before it dropped the second box. So we're going to go 140 times 2 to get a total separation of 280 meters. All right, so now we get more to Unit 2 kinds of questions. So here we have a mixed martial artist. He kicks his opponent in the nose with a force of 200 newtons. Identify the action-reaction force pairs in the interchange. Well, this is a Newton's third law problem. For every action, there's an equal and opposite reaction. So here, the guy's foot is applying a 200 Newton force to the nose, which means the nose, according to Newton's third law, has to apply a equal but opposite force to the foot. So that's looking like D. So the foot applies a 200 Newton force to the nose. The nose applies an equal force in the opposite direction to the foot. Similar kind of question. Joanne exerts a force on a basketball as she throws the basketball to the east. So she pushes the ball. Let's say that here she is. She pushes the ball to the east. So this is the force of Joanne on the ball. We'll say J on B. At the same time, according to Newton's third law, the ball has to push back on her. So force of ball on Joanne. Those have to be equal but opposite. Now, you might think since the ball is pushing back to her on the west that she's going to accelerate to the west. She may not accelerate to the west at all because there's also a frictional force down here on her that may be equal to that force that's pushing on her. So she may not accelerate. She may not move at all. There is a net force acting on her. So that's not going to be true. This is the answer here. The basketball pushes her to the west. She pushes the ball to the east. The ball pushes her to the west. Answer C. All right, now this one's going to be confusing for some of you. So we have some fireflies, identical, put in closed jars, 3 different configurations. So there's 3 in jar A, 1 in jar B, 1 in jar C. The 1 in jar C is just sitting on the bottom. The ones in A and B are flying, and they're just hovering. They're not accelerating. So we want to know, rank the weight of each jar according to the scale reading from heaviest to lightest. So here's the thing. Some of you are going to say that that C is the heaviest because it's the only one that has a bee or a lightning bug firefly sitting on the bottom. But it turns out, yeah, this one's sitting on the bottom and it's pushing on the jar, but this guy to hover is pushing down with his wings with the same force that this guy is pushing down sitting there. So these two have the same weight. This one has 3 fireflies all pushing down. That air is going to be pushing down on the bottom to keep them up in the air. So it doesn't matter if they're flying or if they're sitting there, they're going to weigh the same. So this one is going to be greater than A, and which is also A is greater than B, which is equal to C. All right, so this is a kind of a classic Newton's third law problem. The system shown at the right is accelerated by applying a tension T1 to the rightmost cable. Assuming the system is frictionless, the tension in the cable between the 2 blocks T2 is. So in a problem like this, first of all, you're going to calculate the acceleration of the system. So remember that F net equals ma. Since there's no friction, the net force acting on the system is T1. So T1 is going to be equal to the mass of the system, which is 5 here and 2 here, 7 kilograms times A. So A is going to be equal to T1 over 7 kilograms. That's the acceleration of the system, which is also the acceleration of each object. So now let's look at T2. So T2 is the net force acting just on box, on the 2 kilogram box. So in this case, the net force acting on that box is T2, and that's equal to the mass of the box, 2 kilograms, times the acceleration of the box, which we just established is T1 over 7 kilograms. Kilograms cancel, which means that T2 is equal to 2 over 7 times T1. And that's looking like that is choice A. So you're going to see problems like this on the AP exam, very common basic dynamics type problems. All right, and this is an Atwood machine problem. And what we're trying to do here is we've got these two objects. This one's mass 3 kilograms, this one's mass 5 kilograms, and we want to find the tension in the string. First thing you need to do is to figure out what's the net force acting on the system. And the net force acting on the system is going to be essentially the weight of this box minus the weight of that box. So this box weighs 50 newtons, and this box weighs 30 newtons, just mg, 3 times 10, 5 times 10. So that means the net force acting on the system is 50 minus 30, 20 newtons. So next we want to calculate the acceleration of the system. So acceleration of the system is going to be equal to the net force of the system divided by the mass of the system. So that's going to be 20 newtons divided by the total system mass, which is 8 kilograms. And 20 divided by 8 gives us 2.5. So both of these objects are going to accelerate at 2.5 meters per second square. This one's going to be accelerating down, and this one's going to be accelerating up. So now we want to find the tension in the string. So to do that, we can take either one of these boxes and draw a free body diagram for it. Let's just take box M2. So for box M2, we have its weight acting downward, 50 newtons, and we have the tension acting upward. And we know that the net force acting on that box is going to be remember net force is sometimes shown this way, the summation of all the forces. It's going to be the tension plus 50 newtons. Now, actually, that 50 newtons is downward, so we probably plus negative 50. Always use negatives for your downward forces. All right, so we can calculate the net force acting on box 2. The net force acting on box 2 is going to be box 2's mass, 5 kilograms, times box 2's acceleration, which is going to be negative 2.5 meters per second square. It's negative because it's going to be accelerating downward. So now if we go back up to our equation here, our net force is going to be 5 times 2.5. So that's 12.5. So our net force is negative 12.5 newtons. And that's equal to the tension plus the weight. Solve this out for T. So let's add 50 to both sides. So the tension ends up being 37.5 newtons. And notice it's positive. Well, that makes sense because the tension on box M2 is going to be pulling it up. Let's do the same calculation, except this time let's use box M1. So let's draw a free body diagram for box M1. So we have a weight of 30 newtons, and we have a tension pulling up. And we know the tension force in this case is higher than the weight because this thing is going to accelerate up. Free body diagram again, so the sum of all the forces is going to be equal to the tension plus the weight. Let's calculate the net force on that 3 kilogram box. So F net equals the mass, 3 kilograms, times the acceleration, positive 2.5, because this thing's going to accelerate upward. So let's see, that is what, 7.5? All right, so we end up with a net force of 7.5 newtons, and that's equal to our tension plus our weight. Solve this out for tension by adding 30 to both sides. So tension equals 37.5. Same answer we got before, because the tension in a rope like this is going to be the same no matter where you measure it. So again, a classic kind of problem that you're going to see throughout AP Physics 1. All right, here's our last problem. It's sort of an FRQ type problem. In physics, they love to ask about elevator problems. So here we have a student standing on a scale in an elevator at rest. He sees that the scale reads 840 newtons. Well, if the elevator's not moving, that means there's no net force on the elevator or the student, which means that this number right here, 840, that's his weight. And therefore his mass is going to be equal to his weight, 840, divided by G, 10. So his mass is going to be 84 kilograms. That's his real weight and his real mass. As the elevator rises, the scale reading increases to 945 newtons for 2 seconds. So here's the elevator. Here's the cord for the elevator. And in this case, the elevator is rising up. And notice that his weight seems to go up. That's because this thing is accelerating upward. To accelerate upward, there has to be a net force on the elevator. And since the student's in the elevator, there's a net force acting on him. They're being pushed upward. And the amount of net force in this case would be his real weight, 840, minus the 945, or 945 minus his real weight. So 105 newtons of net force, positive 105 newtons. All right, so then returns to 840 for 2 seconds. So what I'm hoping that tells you is that it accelerates to begin with, and then it starts going at a constant speed. It continues up, but it continues up at a constant speed. And as long as it's moving upward at a constant speed, there's no net force, which means the scale reads his real weight for 10 seconds. It then gets up near the top, it starts to slow down. So when it starts slowing down, its velocity is still up, but because it's slowing down, its acceleration has to be down. And notice that when it's accelerating downward, his weight seems to go down. And that tells us there's a net force of his real weight, actually his scale reading, 735, minus his real weight of 840. So there's a net force of negative 105 newtons acting during that part of the problem. So now let's try to answer the questions. So explain why the apparent weight of the student increased at the beginning of the motion. So the apparent reading is what the scale reads. Seems to go up. It seems to go up because there's a net force acting up on the elevator, a net force pushing the scale harder against the student. That's what we're looking for on A. B, draw the free body diagram for the student while the student is accelerating upward, then moving at constant velocity, and finally accelerating downward. So when he's moving upward, his weight is still acting this way. And then there's an elevator force. We could just think of it like a tension. If he's accelerating upward, that upward force has to be greater than his weight. When he's at a constant velocity, there's still tension in that cable, but that tension has to be balanced out by the weight of the boy in the elevator, something like so. These two arrows have the same length. When he's accelerating downward, the weight of the boy in the elevator are greater than the tension force acting upward. There's a net downward force. All right, then we get to see, sketch the acceleration versus time, velocity versus time, and displacement versus time graphs of the student during the elevator ride. I already have those sketched on the next slide, and let's just go through and talk about them. So first of all, let's talk about the acceleration. So for 2 seconds, he was accelerating upward and moving upward. That means he had a positive velocity and a positive acceleration. That's what we see right here. And notice that that happened for first 2 seconds. All right, then he started moving at a constant velocity, going upward. So for the next few seconds, he had a positive velocity, but he had 0 acceleration. And notice that the acceleration in that time interval down here is nice horizontal line at 0. And then at the end of the problem, he continued to move upward, positive velocity, but he started slowing down, which means his acceleration was a negative value. And that was for the last 2 seconds of the problem. And we see that right here. Negative acceleration for the last 2 seconds of the time interval. All right, now let's look at the velocity time graph. So velocity time graph, remember the slope of this graph represents acceleration. So for the first 2 seconds, he has a positive velocity and a positive acceleration. And we see that here. For those first 2 seconds, the velocity is positive, the slope is positive, which means there's a positive acceleration. Then it gets up to some velocity, and for the next few seconds, the elevator moves at a constant speed, a constant velocity. So we see a nice horizontal line at a positive value for those next few seconds. And then for the last 2 seconds, he still has a positive velocity, which we see the velocity is never negative, but he's slowing down, which means his acceleration has to be negative. And we see that in those last two lines. And remember, the slope represents the acceleration. Finally, we've got the position versus time graph. So remember that position versus time, the slope represents velocity. Remember, in that first 2 seconds, he's accelerating. He has a positive velocity, and he's accelerating. And the way that we see acceleration in position time graphs is we see curves in our graph. We don't see a nice straight line. We see curvy lines. So if you look at the first 2 seconds, we have a line here that is concave upward. That tells us that we have a positive acceleration going on. So again, first 2 seconds, positive velocity, positive acceleration. For the next few seconds, constant velocity. And notice the slope of that line. And remember, the slope of a position time graph is velocity. That slope is constant. So constant slope equals constant, in this case, positive velocity. And then finally, in the last 2 seconds, we start to slow down. So again, positive velocity, negative acceleration. And the way we see that on a position time graph is a curve that is concave and down. So the curve is like that. So that tells us we've got a negative acceleration. All right, so that's it for our session today. Remember, next week's session will be next Friday at 10 o'clock, and we will wrap up Unit 2, and that will be the last of our weekly content reviews for the semester. All right, hope that helped.